So good morning. I'm going to jump straight into essentially where we left off last time. And we're going to look at the chain rule. And all I'm really going to do is try to expand the various kind of permutations and combinations of variables that you could get. So for instance, I'm going to keep the functions relatively simple. There is z as a function of x and y. And this time, x is going to be a function of three variables. R squared plus s t cubed. Y is going to be just r cubed. I'll put in an s. There. Now, in a situation like this, you're likely to be asked to find partial derivative of z with respect to r, or the partial derivative of z with respect to s, or partial derivative of z with respect to t. And the reason why there are three choices here is because between the x's and y's aren't there three variables, even although the y doesn't have any t's, because the x does. This is basically r cubed plus st plus 0t. Yeah, so you could say it had a t, it just were none of them. So let's pick a partial derivative with respect to r. Now you do the partial derivative with respect to x times the partial derivative of x with respect to r. What would be the next piece? Because this particular version of the chain rule has two pieces. This is one of them, but what would the next piece look like? Any volunteers?
The derivative of z with respect to y, and then the derivative of y with respect to r.
Right. So it's still got that same framework. That term, because that's basically two derivatives, two partial derivatives, and doesn't that term essentially tell you the contribution of x that gives you the r variable, and this is the contribution that y does to the answer? Agreed? Now I could have done those two, but I won't. Let's up the ante and assume that z is now not just a function of x and y, but x, y, and w, and that w is r, s, t. Now, in this case here, this would not be the end, would it? Wouldn't we have to add yet one more term? The partial derivative of z with respect to w times dw and dr. Well, let's see what the pieces are. If you differentiate this fellow with respect to x, you get 2x. And if you differentiate x with respect to r, you get 2r. If you do this with respect to y, you get 3y squared. And the derivative of y with respect to r, well, that doesn't matter, so you get 3r squared. And then this term, you get 4w cubed. And then differentiate this fellow with respect to r, you get st. And so in your homework, that would be your final answer that you would do. I think in good math world, wouldn't that x get replaced by these guys, and that y by this, and this w with this? So do you feel comfortable that the chain rule can be adapted to a function of three variables, where each of those three variables was in terms of three other variables or two other variables? So can you imagine there's I mean, it's unlimited. There's, I guess, practical. You wouldn't expect to do a 10 variable function where each of the 10 variables were in terms of 42 other variables, because I mean that would be 420 combinations. I would use up an entire sheet of paper doing it, right? So you're not going to get that as a question, but as a concept, it is possible, isn't it? It's doable. Not that I could imagine any situation that you would ever want to or need to, but it's doable. There we go. So let's beef it up a little bit differently by just making the function.
Can you put that other page back for a second?
Oh, sorry. I'll put it over on the other side. So W is the square root of this ugly guy, and X is going to be T sine theta. Y is going to be T cosine theta. And Z is going to be e to the T theta squared. Right. So it's a classic question. You're going to be asked to find a partial derivative in terms of T or theta in this particular case. I have no particular preference. So can we pretend that you were being asked to find the partial derivative with respect to theta, right? Now that would be made up of 3 pieces. The first one would be the partial derivative with respect to x, and then you do dx with d theta. Then the partial derivative with respect to y, in which case you would get that as your second term. And then finally the partial derivative with respect to z, and you would get that as your last term. We have some calculation issues, I guess, some algebra issues. Would you agree that this function is quite ugly and therefore its derivative might be a bit messy? So I'm going to do its derivative kind of, is it okay to move this page now? I'm going to make, I'm going to look at this derivative, how I would tackle it. The first thing is that square roots aren't really necessary for derivatives. They're not helpful. I'm going to turn it into a half power. Would you also agree that if I'm finding, say, the first partial derivative with respect to x, that this is a chain rule question? And so the partial derivative with respect to x is going to be 1/2 x squared plus y squared plus z squared, and reduce the power by 1. So to the negative 1/2. So I'm using the power rule, 1/2 something to negative 1/2. And it is a chain rule. So don't you finish with the derivative of x squared plus y squared plus z squared, the partial derivative, but with respect to x, which gets me 2x, which means if we tidy these up, they cancel, and you bring this down, you now get an answer that looks like that, which then becomes this answer. And we're using a kind of style point rule, which says that if you're going to do any kind of algebra, derivatives, integrals, whatever it might be, you should always make your answer look in the form of the original. So the original had square roots. It makes perfect sense that I should have a square root in my answer, for instance. Now that guy is going to go here. Agreed? I do not want to have to do a whole load of work for these two guys. And I don't think I need to. Couldn't I use symmetry? Shouldn't I be able to use this answer to predict this one? That's what symmetry will allow me to do. Would it seem reasonable that that's what you would eventually get? And then for this one, so if you can see any shortcuts, any little tricks of the trade that will reduce your workload, and I think that's a reasonable assumption, right? I am sure that's what you would get. Doesn't that like reduce your work a little bit? Now, you might not physically write it down here because you're going to write it over here anyway, but at least you would know where it would go. So I'm going to get x over ugly square root, so I don't have to write it all, times this fella derivative with respect to theta is t cosine theta. And then it's y over ugly square root. This one will get you negative t sine theta. And that last one is z over ugly square root. And this fella just gets you e to the t theta squared. And as far as the homework's concerned, okay, you're not allowed to do dot, 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 but when you write it down, can you imagine that's going to be about this big? It's going to be this guy, xt cosine theta, this guy with a negative t sine theta thing, and this guy with an et theta squared tagged onto it. So you can imagine that term would go here, this term would look like that, and the first term would look something like this. So you can imagine this, take away this, add this, would be the final result.
Would that be 2 theta, since it's with respect to theta for the z?
Oh, respect to theta. Okay, yes. Did you all catch that deliberate mistake?
Yes.
Yes, you all caught it. Good.
Just showing us what not to do.
Exactly. You're picking up my teaching style really easily. I've noticed that. No, I just make mistakes. That's what it really means. In lots of stories or lots of questions that we're going to do, you'll find that I like dot, dot, dot a lot. Not necessarily right now, but in the future, we're going to do some stuff. And then I'm going to say, well, you know where to finish this question. We've got, the hard bit's over. It's like 5 or 6 lines later, you'll have the final result. So I'll just say dot, 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 and you like fill in the gap yourself. So if you ever see me do that, it just means it's an abbreviation for filling in things. We feel comfortable about this process, this chain rule of functions being functions of other functions, and that you can still do partial derivatives, no matter how scary or hairy they may be. Any questions about that, or are we good? We are good. That went really smooth. Just to be sure, it's always a good idea just to be sure. I'm going to go into the homework, and I think I've set it up, so I would be. I got some in chat. Hi, Reese. Nice to see you. Okay. Share. Basic. Is this the right one? It is, I think. Right, so I'm going to just, we'll go through the homework questions, not in the real sense, but just skimming them. Does it feel okay? Does question 1 look all right? Here we've got a function z in terms of x and y, and x and y are only in a function in terms of t. That would probably be a baby one, wouldn't it? Because there's only one variable to do it to. Are we cool with that kind of question? Any questions? Let's look at the next bunch. Here's z as a function of x and y, but x and y are now functions of s and t. We kind of did that type of question yesterday. Here's another one where z is a function of r and theta, and r are functions of s and t. It's a linear one. Oh, I think I'll do this one. I don't think I did anything with a tan. I'll just pick my own version, so I'm not doing the same question, but something dead like it. Okay, here goes. Because I can see something that I haven't done as well, which I'll do in a few seconds. So it was a good idea to check the homework questions. Right. Let's suppose the question is, find the partial derivative with respect to t. So you're going to do the partial derivative with respect to u, du by dt, and the partial derivative with respect to v times dv by dt. Now I only need 2 because this is 2 as well. Are we good? Now, if Z is the tangent of u over v, and you want to find the partial derivative of Z with respect to u, you're going to have to be careful. Trig always causes problems with people, and simple thing like remembering the derivative of a tan might throw you. Does anybody remember what's the derivative of tan x?
I think
Secant squared.
it's secant squared.
It's a secant squared. Now this is a chain rule, so that means it's a secant squared of u over v. So far good? Now, don't you then have to differentiate u over v with respect to u? Partial derivative of u over v with respect to u. What in heck is that? Any volunteers?
One over
The
v.
Repeat
derivative
the
of
question.
this. Yes, the derivative of u over v with respect to u.
Why isn't it
It
one
should
over?
just be 1.
Is it just 1 or is it 1 over v? Because I
Or
think
1
I
over
heard
v,
that.
sorry, yeah.
Right, so we all agree on that, right? Agreed?
Mhm.
Right, now the other guy is also secant squared, u over v. But now we're going to differentiate the fraction u over v with respect to v. And that's a little bit trickier, isn't it? It's not as
Using
simple
it
as
to
1 over v or u over 1 or anything like that. Is it not? I guess you could call it that, right? And if you do a power rule on it, it looks like that. And if you make it look pretty, it looks like that. Are you happy about where I got that from? So it's times the derivative of u over v with respect to v, and it ends up being this rather messy guy that looks like that. And then at this point, I'm going to go dot, 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 plus dot, 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 dot. Isn't it just a matter of putting in the pieces and you're good to go? For instance, du by dt would be 1. dv by dt would be -3. Right? So you'd have this answer times 1 and this answer times -3. I'm looking at don't know if I'm looking at a puzzled face or just a thinking face. Was that okay? I mean, I'm dot, dot, dot it. Do you need to see the lines to feel comfortable, or is it good enough? We're good. I got a thumbs up.
That was good for me.
Okay. If it's not, you tell me, and I'll do it. Now, the guy that I noticed, and I'm glad I went to the homework, and I'm saying, we didn't cover this, is it's a little special, I don't know how you would describe it, as a thinking question. You see these two guys here? Where they give you a table, and the value of the function
can't
or
see
its
it.
partial derivatives. Oh, can you see this thing?
No.
No, we're looking at you.
No. Okay, here we go again. I'm glad you stopped me now and not later. Here we go. Right, so here is a function. And I'm writing this function down because I need to show you what the heck's going on. It's a function in terms of a variable called u and v. And it's f of e to the u plus sine v, comma, e to the u plus cosine v. And we're being asked to find the partial derivative of g with respect to the variable u at the point 0, 0, and then another one at vv. And there's a table, I'm just writing down the table that you can see in front of you. And we'll show you how you can use this table to answer that question. So, there's my pens. Here we go. So, I have an f, I have a g on the top row, I have the partial derivative with respect to x and with y, and at the point 0, 0, we get the answer 5, 3, 1, 7. And at the point 1, 2, you get the answer 3, 5, 0, 9. So I've basically just copied what you've done there. After I've done question 8, you will be able to do question 9. It's just another version of it, so you get practice at it. While we're here, these guys here are pretty much just what we've been covering, right? Different versions of partial derivatives. And that's about it. Yeah. Okay. So here goes. No, it isn't. I got it. There. Now it is. Right. What we're going to look at here is how this table can be used to find this one particular derivative. And it's not clear because of the information what's going on. So let me tell you what's really going on. You have got a function x, and x is a function of u and v. So basically I'm seeing that as my x and I'm seeing that as my y. That's not very clear, but that's exactly what's happening. And you have to realize that or the thing's not going to work. Now they've called this function g of u, v, but actually isn't g also a function of x and y, where x and y are functions of u and v. So that's not obvious either, but that's what's happening. So when they say 0, 0, right, for instance, what are they asking us here? Well, they're telling us that u is 0 and that v is 0. Well, if you find 0, 0, you're finding the value of the function f at e to the 0 plus sine 0 and e to the 0 plus the cosine of 0. That's 1 plus nothing, and that's 1 plus 1. So if you're wondering where the 1, 2 comes from, it's coming from here. Right, now, if I asked you to find that fella, I'm asking you essentially to find dg by du, agreed? And that's going to be equal to the partial derivative with respect to x, and then the partial derivative of x with respect to u, plus the partial derivative of g with respect to y, times the partial derivative of y with respect to u, right? So that's my general. Now, normally these would be expressions in x's and u's and v's and whatever letters we're going about, but they aren't going to be that. They are going to be numbers coming from here. And what's the only thing I know? Well, I know that we're being asked to evaluate it at that guy, okay, which is the same thing as x equals 1 and at y equals 2, which is that guy. So there are two different things going on here. Right. The partial derivative of g with respect to x, the partial derivative did I write that table down right? Let me have a quick look. I think I'm missing something. No. No. Okay. Where's F coming from? I am wrong. I definitely wrote something down wrong because it ain't working the way it's meant to be working. Oh, there's G and there's F. Oh God, that is sneaky. Exactly, it's two different functions. Everything is fine. I just didn't realize what was going on here. Okay. So if you want to do the partial derivative of g with respect to x, you're basically doing this guy with respect to x, so you're finding this fella, so he's 1, and dx by du, well, if you differentiate dx by du, you've got this fella, and that's going to be e to the u plus cosine v. And you want to do dg by dy, which is the same as this guy, which is 7. And then dy by du, which is going to be this guy's derivative, which is this. And then all I need to do is replace the u with 0.
Excuse me, I think you did the dx by du incorrectly.
I did.
But you did it by v. Shouldn't the sign v go away?
Yes, it should. Without start again. This fellow with x is 1. It's not this hard. I'm just confusing myself because I can. This fellow is x, so you're only going to get e to the u. dg by dy ends up being the same as this fella, so it's 7. And we're going to get the derivative of y, which is what, e to the u, which gets you 1 and 1. God, that was a lot of work. These are zeros, so e to the 0 gets you 1, so 1 times 1 and 7 times 1.
No.
I'm getting a lot of no's there.
Yeah.
Hey, maybe your sound. Maybe
Oh,
one
sorry.
no.
Oh, sorry. I didn't realize my mic was on. Sorry.
Okay. I'm assuming that is not a good sign. Let me take a note of that question, and I'll find a shorter, more clearer version, because I'm sure that wasn't as clear as it could be. Right. Now, there's really only one other question in that set that we haven't talked about yet, and that is that there is an overlap between the chain rule and implicit differentiation from Calc 1. Way back in the day, that would be in Calc 1 an implicit function, right?
We are looking
And
at all of us and not the
I am doing that again. This fella here would be implicit function in Calc 1 world. Now, if I asked you to calculate dy by dx here, would you agree that that would be a lot of work? More work than you perhaps want to do.
Yes.
Right. So let's look at that. By thinking of this being written in this format. This is the function of x and y, and it's equal to, in this case, 10. Agreed? Now, if I find the partial derivative of x, right, which is df by dx, I can go through this particular situation, and I can prove you that it's equal to that guy. So I'll write it down a little bit clearer. If you want to get dy by dx, which is essentially what that's equivalent to, you can get it by doing the partial derivative of our function with respect to x divided by, I don't know why that's going capital on me, it shouldn't, by that. Now, you want to see a proof of that that's not really a proof, but it kind of shows you what's going on. Do you know, from time to time, don't we look at these things as they were almost fractions? I know they're not, but they are, like, in a sense, like a fraction. If I take this guy and you divide it by that guy, isn't it the same as taking this guy and multiplying him by that guy? And do you see that they cancel out? And can you see the dy by dx thing? So what does that mean? That means I can find dy by dx by just taking the partial derivative with respect to x of this fella and dividing it by the partial derivative of f with respect to y. You might wonder where that negative comes from. Well, if you're doing the real math, one side would have to get moved over to the other side and become negative before you divided it. So it's a kind of trust me thing. Okay, let's see what that would be. This fella here then, if you want to get his derivative with respect to x, you take, it's a negative of partial derivative with respect to x, 2x plus y cubed plus sine y. On the bottom, the same function, but now the partial derivative with respect to y. In this case, you get nothing. In this case, you get 3xy squared. In this case, you get x cosine y. This function is equal to that. That's its partial derivative. And that's a Calc 1 question. Is that not amazingly easy to do? If you go back and you look at how you would have to do that in Calc 1, trust me, wouldn't it be at least 2 or 3 times more work?
Yeah.
Yeah, try another one. Suppose I have the implicit function x squared e to the y plus y cubed sine x equals 1. Think of this as being your function. Then the implicit differentiation, dy by dx, of this fella is negative. Do the x's on the top. Oops. Yeah, plus. And do the y's on the bottom. Yeah. Less than 1 minute, I have just found the first derivative of a really ugly implicit function. I think that's kind of cool. Any questions?
Would that work if there was a z term as well?
No, unfortunately. Only works for x's and y's, implicit combinations of just x and y. So it's a nice trick. And it works for Calc 1 questions. I guess what probably I would have thought is, why didn't you just tell us this in Calc 1? Instead of us having to do all this horrible algebra that is the method you'd have to use. If you wanted to do this from scratch, right, in the Calc 1 way, you'd probably end up using this piece of paper here to do it in, right? And lots of messy bits. Instead, it's just simply top derivative, bottom derivative, and stick a negative in front of it and you're done. Well, the reason why we don't tell you is, you know, a little knowledge is a dangerous thing. And if you find out how to do partial derivatives, because you'd need to know how to do that to be able to do the shortcut, isn't there a very bad temptation that you start using partial derivative techniques when you shouldn't? So there are lots of little cool things that we will show you in the future, in your future math career, that you've not been told yet, because it's dangerous to know things before you're ready. So that was a little trick.
I actually used that little trick on a function with 3 variables for the homework, like the last homework, and it worked for like 3 problems.
I never knew that. That is cool. I'll have to have a look at
Yeah.
that sometime. So what was the adaptation with 3 variables?
It's basically the same exact thing. You just have to make sure you know which partial derivative you put on the top and the bottom.
Oh, okay. So one of the functions is considered the dependent variable, it sounds like, and the other
Yeah.
2 are considered true. Right. Yeah, I guess. I've never seen that. I should look at my... the homework questions are partially generated by the software. I just go in and add or take away some, but evidently I didn't pay attention to that last one. So it looks like a good question. Was it easy to do once you figured that out?
Oh yeah, I looked up the little formula to do it, and
Oh, okay.
it was super easy.
That's great. As long as they tell you a formula, you don't really need to worry too much about the details. Did they also tell you the formula that for the one I just told you for the dy by dx version?
No, I think I looked up both of them by myself because I just didn't know how to do it, and I was trying to do it before you taught us.
Yeah, you were kind of a day ahead of us, which is not a bad thing.
I just want to make sure I understand something. So, when we're doing this trick, is it always just gonna be you stick a negative in front of it?
Yeah.
Is that always gonna be the case?
Yes.
Even if there's like a third variable like a z?
I haven't seen the Z one, so I can't
Well, for me, I
vouch for
set
that.
and it worked, but I'm not sure it works for all of them.
Okay. For the ones I've just shown you, the XY version, it's definitely always negative. That I can say for sure. And the other one, I guess you'll find when you see the formula. Okay, that then is pretty much the end of that section. So what we're now going to do is we're going to look at a special kind of derivative, and it's called the directional derivative. And I know I've gone out of screen again, haven't I? So what is a directional derivative? What is it, I guess, is what I'm trying to mumble to myself. It's a little bit hard to visualize. I'm going to do my best, and I'll probably fail miserably, but I'll try. Can you imagine a surface that looked like this? I'll put some kind of projection lines on it over you. Can you imagine that surface is like the top of a hat? You know, one of those little monk hats, the caps, right? To give you a visualization. So imagine we had this surface. And this function here is z equals a function of x and y, right? Or pretty standard, that's the only guys we're going to worry about, right? Z equals a function of x and y. If you think about what a directional derivative does, is it's closely connected to what we've already done. When I do a partial derivative with respect to x or a partial derivative with respect to y, I'm essentially doing a directional derivative. This one is in the x-axis direction, and this one is in the y-axis. So you imagine what you're doing is you slice it parallel to the y-axis. That's what dz by dy is. And then if you plug in a value for x and y, it will tell you at that one specific point what the slope of the tangent line is. Well, what a directional derivative does is that you have a vector, let's say the vector 1, 2, and you slice the shape in that direction, right? So you're traveling in a kind of start at the origin, go 1, 2. So you're kind of doing it in, yeah, I told you I would make a mess of it. Can you imagine that line is the vector 1, 2? So you can imagine taking the surface and going in a particular direction along that surface. That's what a directional derivative is. It allows us to tell things like, if you're on the point of a surface and you go in the direction 1, 2. So you choose any point on the surface and you go in this direction. The number that you get back, because it's a derivative, is the slope of the curve in that direction. Can you imagine that it was a hill and you were standing at this point on the hill and you were deciding that you were going to walk in that direction over there? Wouldn't you be either going uphill or downhill according to some slope? That's what you're calculating when you're getting the directional derivative. So if the directional derivative ends up being 0, aren't you basically walking horizontal to the earth? You're not going uphill, you're not going downhill. If the directional derivative is negative, aren't you going downhill in that direction? And if it's positive, you're going uphill. So how do we calculate these little guys? Well, directional derivatives have a formula. And I'm getting this guy here because I want to make sure I'm using UVs and all that other good stuff instead of just my own lettering and then have to change it. So this is section 14.6. Actually, I am going to show you the textbook because they can draw pictures much better than me, and it might give me a chance to have another shot at describing what's going on. Where are you? Okay, I've lost you. Oh, you're over there. Okay, so this is straight out of the textbook. I'll try this. My computer is really slow right now. I'm not sure what's going on. Nah, I was hoping their picture would be just as good or as bad as mine, but it's not really. Can you imagine this is the hat that I had? Guess it's a little bit better picture. Do you see this line, this point P? This is a point on the surface that you're going to get your directional derivative of. If you imagine this red line here is the tangent line, and you are getting that line is in the direction that you're going to do your directional derivative in. And they use the letter vector U. Okay, so that I needed to know because I was going to call it V. And then there's a whole load of theory coming up where they go through a bit of page and eventually we get, I'm just writing down this notation. Okay, gotcha. Okay, the directional derivative is called capital D, little vector U, of whatever the function is, and U is the vector A comma B. And you plug in partial derivative of xy times A plus the partial derivative of y times B. So, okay, that picture didn't help one bit in my opinion, so I'm kind of disappointed. You're just going to have to trust me on this one, that a directional derivative is just a derivative in a particular direction, and it's a number that tells you how steep a hill is at a point. Will we go for that? It's how steep a hill is at a point. So let's suppose I have a surface, x squared plus y squared. And let's suppose I want the directional derivative in the direction 1, 3. How would I get the directional derivative? Well, that's the notation that says what the directional derivative is. It's d of vector u, the function, and it's equal to this fella. That's the partial derivative of xa plus the partial derivative of yb. In this case, 2x times 1 plus 2y times 3. So the answer would be 2x plus 6y. So we have just found our first partial derivative. Suppose I wanted to know the partial derivative at one particular point. So can you imagine it was that guy again, right? And the point I want to know is here, traveling in the direction 1, 2. What would that look like as a number? Well, the directional derivative at the point, well, I need to know a point 1, 2. It's there. It would be 2 lots of 1 plus 6 lots of 2. That's 14. So at that particular point, if I was on a hill that was that surface, and I was going to walk in the direction of this vector, I would be going up a steep 14-unit slope. So that mountain is pretty steep there, right? It's got a gradient of 14. Are we good?
Yep.
Okay. I think the application is probably easier than trying to explain to you what you're finding. Right? It's easy to do it, even if it's not so clear what you are finding when you've done it. I'm going to change the rules a little bit.
Wouldn't this be a good time to do attendance?
Oh God, is it that time already? This would be a great time to do attendance. Why don't you do attendance while I set up this new guy? So you've got about another minute. It's 36 people here, it looks like. Okay, to finish today, I'm going to take the formula for calculating a directional derivative, which is this formula. It's the partial derivative of x times a plus the partial derivative of y times b, where u is the a and the b. And I'm going to change it by giving you some new notation. There's a guy called delta f. And delta f is a vector, and it's equal to this fella here. It's called the gradient. So the gradient function, delta f, is equal to this fella. Now what that allows me to do is it allows me to take this formula here and rewrite it as a dot product. If you take this guy and you do a dot product with this guy, don't you get this formula? So do you see that this here is equivalent to that? Just to remind you then, right? If you do delta f, it's a partial derivative of x, comma, right? The partial derivative of y, that's the vector. If you do a dot product with a comma b, isn't the dot product multiply these two, add multiply these two? And doesn't that get you fxa plus fyb? I think this version of the direction derivative formula is much more concise and just looks better in my brain. Dot product. I think this is us for today then. When we come back next time, I'm going to have put online by then.